Okay, welcome everybody to a short lecture on linear systems by matrix methods. So we already saw how to solve a linear system of the form. So let's say we have n equations in n unknowns, because this, actually let me call that B1, and you keep going like this till you get a n1 x1 plus an2 x2. So my x's are my unknowns. All the a's are real numbers, they're coefficients. And the b's are real numbers as well. So you have, in this case, I'm going to have n equations and n unknowns. Now, the Gaussian elimination has lots of advantages, but one advantage in particular is that it can handle different numbers of equations versus unknowns. The method I'm going to show you here is strictly for the case where you have the same number of equations as unknowns. Okay, so I can write this system. Let me call this 1. 1 can be written as, let's call this one 2. AX equals B, where A is the matrix A11 up to A1n, AN1 up to ANN. B is the matrix, is the column vector B1 up to Bn, and X is the column vector of unknowns. Okay. So if you check that matrix multiplication makes sense, it's an n by n times an n by 1. That gives you an n by 1, and B is an n by 1. Okay. Okay. Why write it like this? Well, and how can we solve it by matrix methods? Well, suppose A is invertible. That means A inverse exists. Okay. And when does A inverse exist, by the way? A inverse exists exactly when the determinant of A is not equal to 0. So A is invertible, means A inverse exists. And for A inverse to exist, you need the determinant of A to be non-zero. Okay, so if A is invertible, then I can multiply my original equation by A inverse on the left. And I can do that as long as I know my left hand from my right hand, and I can multiply on the left by A inverse at the same time. Okay, now a matrix times its inverse gives you the identity matrix. So that gives me the identity matrix times X is equal to A inverse B. And the identity matrix times any matrix gives you back the matrix itself, as long as the sizes are right. And the way we define things, the sizes are okay to make this work. So then here's the solution. So this is the solution of 2. It's this when, oh, let me not say if, when A is invertible. Okay. All right. So now suppose you're looking at a homogeneous system. What does this method tell us? So suppose we look at the homogeneous system. That just means all the equations have right-hand side 0. Okay, so we have this. All right, so now we write our matrix A is before. So let's call this one 3. We're just going in order. Notice it's 1 with all the right-hand side is 0. So here our matrix B is just the row vector, the column vector rather, of all zeros. Okay, A is the same as before, and X is the same as before. Okay, so 3 is the same as AX equals the 0 matrix. Okay, so if A is invertible, by the calculation we just did, X is equal to A inverse times the 0 matrix. But anything times the 0 matrix is going to give you the 0 matrix back. That is X1, all the components of X individually are all 0. Okay, so in other words, the only solution to the homogeneous system three, when A is invertible, is the 0 solution. Is that all the unknowns are each equal to 0. Okay. All right. So that's going to be important for us later when we study eigenvalues and eigenvectors. So what does that mean? Let's take another perspective on that observation we just made. So suppose we want at a system. Suppose we look at a system. AX equals 0 and A is not invertible. Okay. Well, then the previous calculation doesn't work because A inverse doesn't exist. So then we have the possibility of a non-zero matrix X, which solves AX equals 0. Okay, you can't write the formula directly. You just have to work it out case by case. Okay, but this will be important for us later because when we start to find eigenvectors, we're going to need to know how to solve, and I'm getting a little ahead of myself here, but if lambda is an eigenvalue of A, and maybe you've watched that video before, or we talked about it in maybe a homework session. If lambda is an eigenvalue of A, then to find the eigenvector corresponding to that eigenvalue, you have to solve this system of equations. Okay. So what do you need for that to be true? You need that the determinant of A minus lambda I is 0. We need this, or else the only solution would be X equals 0. And the 0 vector can never be an eigenvector. So this way of solving a matrix system is not really useful in general. Nobody wants to solve it using the first thing we wrote down. Look, finding the inverse of a matrix is much harder than just going through the elementary row reduction that we talked about, the Gaussian elimination. But for the theory, it's important to know that you can do this, and also to know when you can solve this homogeneous system of equations and hope to have a non-trivial solution. Okay. And the only way you can solve this and have X something other than x equals 0 as a solution is to have a be not invertible. And that means its determinant must be 0. Okay. All right. So that's the point of this little lecture. Hope you find that helpful, and I'll see you again soon.